The purpose of this video is to discuss hypothesis testing as presented in Chapter 9 of the Jago and Kelly textbook. First, in front of you, you'll see I have a list of homework problems there, and so those are the homework problems I think it'd be a good idea that you practice as we go through this material. I have a couple of examples that I've actually pulled into the lecture so that I can kind of show you how to do it with respect to hypothesis testing. But this chapter, probably more so than others, I would argue it can sometimes be confusing. Hypothesis testing by their very nature are a little bit confusing. So the learning objectives for this chapter are basically that we're going to define what the null hypothesis is. We'll talk a little bit about type 1 and type 2 errors, and then we'll learn how to conduct hypothesis testing using the p-value approach, and also we'll talk a little bit about the critical value approach. So each of these things I'll cover specifically, and when we finish you should feel pretty confident about these things. So the first thing about hypothesis testing to get your head around is this idea that the null hypothesis is the presumed state of what is. I don't know about you, but for me the idea of null sort of suggests not, but indeed in hypothesis testing it is the known status quo, if you will. So whenever we conduct a hypothesis test, we're most often trying to reject the null. We want to show that, hey, we always assumed this to be true, but we're going to show that this other thing is actually true. So first and foremost in all of this, knowing and understanding that the null hypothesis is the presumed default state of nature is very, very, very important. The second thing to keep in mind is there are two possibilities with the null with hypothesis testing, and that is to have the null hypothesis or the alternative hypothesis. The alternative hypothesis is usually the contradiction of the default state of nature. So this is what we're trying to test and show, that this actually works better than that, and it is indeed what you're trying to show in your study, because in many cases we're trying to establish that something is actually new and different and works better this way than the previous way. In hypothesis testing, they keep it pretty short and sweet. We either reject the null or we do not reject the null. So we reject the null when we show that our idea that we're testing was indeed correct, or the alternative was correct. So please keep in mind that at no time in any of this are we ever proving anything. We just might have, so here's some good words, we have sufficient evidence to suggest our alternative is a better summary of our findings than the null. In other words, whatever it was we were trying to test was actually a better summary than what we had previously presumed, which was the null. Now, we either reject the null hypothesis in the case where we are choosing the alternative, or we do not reject the null hypothesis. So in the case where we do not reject the null hypothesis, there we simply have found that our data is not inconsistent with the null. In other words, whatever we are testing is not really different than the null. So we have not found evidence to reject what we normally assume to be correct. We have not proved that we're right, rather we have just not found sufficient evidence to assert that the alternative is a better explanation of things than our null hypothesis has been. Now, I think the best way to explain this is with an example, because I think in theory it tends to be a little bit confusing. So I'm going to talk a little bit about the types of tests, but rest assured we will get to a concrete example that you'll be able to sort of follow and understand better. So when we conduct hypothesis tests, we either do a two-tailed test or a one-tailed test. Basically, the null hypothesis always contains the equality, but sometimes we're going to say that mu of this group is equal to mu of that group versus the alternative where it is that they're not equal. In that case, we've got a two-tailed test because we're interested in either way. It's just not equal. It could be greater than, it could be less than, but it is definitely not equal to. Then the other option is a one-tailed test where we're saying that our outcome, whatever it is less than what we expected, or it's going to be greater than what we expected. But again, the null will retain the equality, so whatever the null is, you notice it's always going to have the line at the bottom or the equal sign. And it just depends on if we're talking about greater than or less than, it just depends on the scenario. But the important thing here is to understand that we can do a hypothesis test for one or two-tailed tests, and either way, two-tailed or one-tailed, the null remains the the null always keeps the equality. So let's just go ahead and do an example just to sort of make this thing more concrete. And this is a pretty basic example. A trade group predicts that back-to-school spending will be on average $600 per family. A different economic model would be needed if the prediction is wrong. So basically, this is a two-tailed hypothesis test suggesting that the spending is going to be $600 per family. We're not talking about greater than or less than. We're saying each family is going to spend exactly $600. So our null would be that the spending is 600, and then our alternative would be that the spending is not 600. I mean, that's how we would set this up. Now, if we wanted to set up an example of a one-tailed hypothesis test, here we could use it something like this. So in this case, we've got this weight loss clinic, and of course we know that weight loss is, just as it is stated, loss, not gain. So a weight loss clinic suggests participants in the program lose on average more than 10 pounds. So since the average diet, we assume the average diet programs really don't work, the null assumes that the program will not work. So the null assumes that the average weight loss is going to be less than or equal to 10 pounds. That's the assumption. But we are trying to show that our alternative is actually correct, so that our mu will be greater than 10 pounds. So in this is a one-tailed hypothesis test because we're interested only in the people that lost more than 10 pounds. Now, another objective of this video is to talk about type 1 and type 2 errors. So a type 1 error is when we reject the null and it is actually true. So essentially, this is like a false positive. We say, you go to the doctor, you get this test, and the test says, oh, you have X disease. But indeed, you really don't have it. But the test showed that you did. So it isn't that the doctor's lying to you, the test gave what's called a false positive. This occurs like if we have send an innocent person to jail because we rejected the assumption that the person is innocent, because we always assume people are innocent until proven guilty. And so I sometimes refer to this as the Shawshank Redemption error, because the guy in the Shawshank Redemption got improperly accused of murder or whatever it was and was sent to prison for a gob of years. And so it's easy for me to keep it straight when I think of it being the Shawshank Redemption error, because he was innocent, but he was falsely accused as being guilty. Now, a type 2 error happens when we do not reject the null and it is indeed false. So it is a false negative. So we say you don't have the disease, you get your test and it says, oh, no, you're fine, you don't have the disease, but lo and behold, you actually do have the disease. So it's, if we equate it to the court system, it would be when we set a guilty person free. So we do not reject the null in favor of the alternative. And I don't want to make any assertions. I mean, I can certainly think of a few people that I think probably should have gone to jail that didn't, but I don't want to, throw that out there. But, basically think about, a situation where this could have possibly occurred. I'm sure you can think of your own examples in your mind. Now, I kind of carefully left off the last bullet on both for the type 1 and the type 2 error, but I'll go back to that now. I did this on purpose because first you kind of have to get your head around what a type 1 and a type 2 error is. But then you have to understand that the probability of a type 1 error increases as we change our alpha, because our alpha is our rejection region. So the smaller our alpha is, then the less chance we have of a type 1 error, because we have such a small rejection region. But when we think about a type 2 error, the opposite is actually true. So the more stringent that we make our rules about who is guilty or a false positive or whatever, then the chances of a type 2 error actually increase. And if you think about it, it makes perfectly logical sense, because we're so careful not to falsely accuse somebody that we then sometimes let guilty people go free. And so it's just kind of the trade-off between type 1 and type 2 errors. So here's an example that uses the type 1 and type 2 errors. So we know that a polygraph is about 95% reliable in determining if individuals tell the truth. Thus, there's a 0.005% probability that a test erroneously detects a lie when the individual is telling the truth. So what is the probability of a type 1 error? Well, the probability of a type 1 error is over here. It's about 0.005. That's our alpha. What's the probability of the type 2 error? Well, we know that the polygraph is 95% reliable, so it's going to be 1 minus our 95, or 0.05. So what are the consequences of a type 1 or a type 2 error? Well, type 1 is going to conclude that the person is lying when he's really telling the truth, which wouldn't be good. And a type 2 error is going to conclude that the individual is telling the truth when the person is actually lying. So neither are good. Now, remember that when we talk all this about type 1, type 2 error, I think sometimes it gets lost that this is 95% of the time it's right. There is no error involved. So we're only talking about the small fraction of times that we create an error. And so, there's always the chance that we have no error. So that's why I made this table here. And you can see that where it is red is where the errors occur. But these over here, these are fine, right? There's no error occurring. This is the correct decision. We reject the null, and the null hypothesis is false. Or here, we do not reject the null, and the null hypothesis is true, and indeed, we're correct. So there's 4 alternatives that you have to consider, so don't forget about the correct decision, if you will. Now we're going to turn our attention to hypothesis testing using the p-value approach. So if you need to pause the video and sort of synthesize this a little bit, of course that's perfectly fine. You might want to try some of the homework problems. It's the problems that are in the single digits. All of those deal with type 1, type 2 error, and hypothesis testing. So in this example, we're going to do a one-tailed hypothesis test using a p-value, which you guys have done before, so you're probably familiar with what this means. So basically the problem talks about the average retirement age is known to be 67 with a standard deviation of 9. So the sociologist wishes to establish that the mean retirement age is actually greater than 67. So he thinks that people that retire are actually 68, 69, whatever. And in particular, the sociologist is using a sample of 25 people to test his hypothesis, that testing the assumption that retirement is actually 67 or less, and he thinks it's actually greater. So his alternative hypothesis is mu is greater than 67. So he sets up this z computation, which we've done before. So he says that in his sample, he finds out, in his sample of 25 people, he finds out that his average is actually 71. And so he subtracts that from the mean, which is 67, and he divides by 9, divided by the square root of 25, because he has a standard deviation of 9, but he has to account for the fact that he has this kind of small sample of 25. So when he does this, he gets 2.22. So remember back from, just a basic z-chart interpretation, we are talking about a value that's 2.22 standard deviations away from the mean. So the p-value on that, of course, is quite small, about 98.3, so, or excuse me, 98.7, and so then that means that the actual chances of it occurring are about 1.3% chance of error. So that is sufficient for us to say, nope, we reject the null in favor of the alternative. Indeed, the average retirement age is older than 67. And if you think about this, all it's doing is, we found this number 71. We know 71 is obviously not the same as 67, but what we want to know is if this difference of 4 is sufficient for us to say, yeah, you know what, the average age is actually trending upward. So if you kind of think about that, I think that could kind of resonate and help you kind of get your head around it. Now here's another example, similar as the last one. This one provides a little bit more information. I think it makes it a little clearer. But anyways, the average obesity in our country is 33%. And we've got an N of 200. And what we want to know is if our finding at our clinic is any different than what the population is. So in our clinic, we found that we had 84 kids that were obese out of our 200, or 42% of our population in our clinic are obese. So we're essentially checking to see if 42% is actually statistically different than 33%. I mean, of course, we can do the math and we see that there's a difference, but we're testing it to see if, it just could have happened by accident, essentially. So what we do is we take 84 divided by 200, and that's where we get our 42%. We subtract from that the average, which is 33%. And then we have to also compute the standard deviation of the average, or how much does our average normally vary. So we just take the 0.33 and we do 1 minus 0.33 divided by our sample size, which is 200. And what we find then is our z-value is 2.71. So we stop for a minute and we think about 2.71 standard deviations away from the middle, so that is pretty far out in the tails actually. So we can probably look at that right now and say, I bet you it's going to be in the rejection region, but we aren't absolutely certain, but we know 2.71 standard deviations, well, that's going to be further out than the previous example we had. It was only 2.22 and we rejected that one. So here we have a graphic interpretation of the results. So our number 2.71 is out here. I sort of tried to draw it in there. You can kind of see we have 2.576. This is our rejection region with a alpha of 0.01. It's just a set number. And our value, which is 2.71, falls in the green area right here, so it's outside of the border, so it's in the rejection region, if you will. So we reject the null hypothesis, and essentially we interpret it as, over here I wrote it out, in this case we reject the null hypothesis. The null had stated that the percent of obese children at the clinic was not different than the national average. Our value of 2.71 suggests a likelihood of obtaining an average of 42% by chance is about 1 minus 0.9964, or not very likely, 0.003, which is less than our 0.005, so we reject the null in favor of the alternative. So we could say that indeed these data suggest that the weight of kids at this clinic is indeed different from the population. Now we can't say all kids are obese or we proved anything. All we can say is that the kids in this clinic are different than the whole population. So here we have a homework problem, number 22, and it says in the problem that people spend on average $130 per trip to Costco, and a survey of 25 customers found that the sample mean was actually $135, and the population standard deviation was 1050. And the data is normal, and the competitor wants to know if people actually do spend more at Costco. So before we do any math, let's just pause for a minute and look at what this is saying. We did a survey on 25 people, and we found that those people on average spend $135 versus $130. But our standard deviation is 1050. So what do you think? Do you think that this is going to be statistically significantly different, or do you think that it's going to be the same? I mean, it's always a good idea, I think, to pause and sort of think about it, because it isn't really all that far away from 130, but our got a 25 people, so that gives it some weight. So let's just take a look here at the answer. We had to do all these things. So calculate the value of the test, statistic, calculate the p-value, and at 5%, what's our conclusion? So here we go. We have our null is set up that mu is less than or equal to 130, because that's what we had said, that the average person is $130 at Costco, and our alternative is greater than 130. And then our test statistic, we run our little test just like this. We don't have to use a p, because in this one we don't have a proportion. We do 135 minus 130 divided by 1050 by the square root of 25. And we find out that our z-value is 2.5. So we're 2.5 standard deviations from the norm. And so we do 1 minus that, and we get 0.0062. So our number, 0.0062, is indeed less than this 0.05. So we can indeed reject the null and say that customers at the store do spend more than $130. So even though it's within the standard deviation, we can still reject it. And the reason is because of the n. The larger the n, essentially what happens is it makes the standard deviation a little bit smaller, and so it enables us to essentially have a better sample. It's more representative. So, but just think about if we had an n of 1, then we'd have a standard deviation of 1050. If we had, say, an n of 4, right, then we would take the square root of 4 and we would have 2, and so now our standard deviation would be 525. So see how that changes it. But an n of 25, I guess, is sufficiently large to suggest that 135 is indeed statistically different than 130. Which is why you have to be careful about the power. When you have a large n, you can pretty much get your numbers to say anything. So just a word of caution there. So indeed we can reject the null, and then if we use an alpha of 0.05 and a critical value of 0.05, we know that 2.5 is indeed larger than 1.645, so we again reject the null. And we find the same conclusion as we had found before, that customers at this store do spend more than $130. So I thought I would do another one that's a one-tailed test, because sometimes those can be a little bit confusing. So we have this advertisement, and it says that the braking distance for a small car traveling at 65 miles an hour is 120 feet. Okay, and a researcher wants to test this, so she randomly test drives 36 small cars and determines that their mean stopping rate is 114 feet with a standard deviation of 22. So just imagine for a minute, we get in 36 different small cars, and we go 65 miles an hour, and we slam on the brakes, and we test to see how long it takes us to stop. So we find that our test is 114 feet with a standard deviation of 22. So that's a fair amount of variation that she found in this. So we want to test the null and the alternative, and then we want to calculate the value of our test statistic just like we did before, and then we want to use the standard value of 0.01 to determine if the braking distance actually differs from 120 feet. So it's a little like the Costco problem, except for we've got a two-tailed test, and the other one we had a one-tailed test. And so the first thing we want to do, take a look at here, we have our mu is 120, and we want to show that our mu is actually not equal to 120. So we set up our test statistic. Our z equals 114 minus 120 divided by 22 by 36. So we end up with a z value of negative 1.64. So with a p-value of negative 1.64, that is only one side, and so we have to multiply that by 2 because, of course, this is a two-tailed test. So we look up our negative 1.64 on our z-test, and of course that's only one side, so we multiply that times 2 and we get this 0.100. And since 0.101 is greater than 0.01, we cannot reject our null. The average braking distance is not actually significantly different from 120 feet. It says miles, but it should say feet. Then down here, we want to test the same thing using this 0.01. And then here we've got these critical values. We've got this 2.576 on both ends. And the decision rule is this, we still have the same z value. We have our 1.64. So we still are going to, we can't reject the null because our value falls inside of that region. It's not enough to reject the null. It's just not far enough away. Now, we could modify this problem and make it work if the lady would have tested more than 36 vehicles, for example. Then we could possibly attain a z value that would get us out into the rejection range. But as it is not sufficient. So with all of this, then what you should do is take a look at these homework problems and try to work through them, and of course bring your questions to class. But your questions will be much easier to help you with if you really put your heart and soul into working on the problem. There is just no substitute for sitting in a quiet room and reading through this and listening to this video and trying some of these problems. It's a difficult concept to get your head around. I suggest some graph paper and some graphs and drawing things out and trying to understand the way these rejection regions work. I just can't emphasize that enough. Some of you, you just are going to have to practice it, and if you don't practice it, it's going to be a struggle. Everything we do now, from all the way to the end of the semester, will build on hypothesis testing. So if you are confused by hypothesis testing, you've got to get it down. So take the time right now to get the hypothesis testing down. It's really important.